This is the beginning of Lecture 3. Lecture 3 is from Chapter 14. This video is going to be Part 1, and it's just going to give you a simple introduction about chemical equilibrium. When we're talking about describing chemical equilibrium, depending on the conditions of a reaction, the direction and rate of the reaction can vary. So there is something called dynamic equilibrium. It is a situation where there is a mixture of reactants and products. And the mixture of reactants and products is due to something called chemical equilibrium, which is the state reached by a reaction mixture when the rates of forward and reverse reactions have become equal. Okay? So oftentimes in terms of equilibrium, we will use a double-headed arrow like you see here. And so in this reaction, carbon monoxide is reacting with hydrogen gas, and it's forming CH4 methane and H2O water. Okay, but this forward reaction is actually represented by this arrow here. This is your forward reaction. But in the same container or reaction flask, another reaction is happening wherein CH4 and water is reacting together, and it is producing carbon monoxide and hydrogen gas. So there is a reverse reaction of this being interconverted or converted back into the reactants. And both of these reactions are happening at the same time in the reaction flask. Because both of these reactions are happening at the same time, at any given time during the reaction, there is going to be some of the reactants and some of the products in the container. This is a situation of dynamic equilibrium. So looking at that same reaction, and this is just going to try and give you a pictorial or molecular representation of what is going on. The experiment begins with a flask or a container with 1 mole of carbon monoxide and 3 moles of hydrogen gas in a 10-liter vessel. So that's what you see in A here. You see some of your H2 gas. So this is your H2 gas, okay? And this is your CO gas, okay? And so it's reacting together, and at the beginning, all there is CO and 3 H2Os, and hydrogen gas. Okay, so carbon monoxide and hydrogen gas. As these two react together, it starts to form CH4. CH4 is here, okay, and some water. Okay, because it hasn't fully reacted, of course, there's still some hydrogen gas, and there's still some carbon monoxide left in the container. Okay, as the amount of CH4 and water increase, because it is the product and being produced, they react together and form carbon monoxide and hydrogen. And so it's a competing reverse reaction. Okay, and so if you're looking at this graph here, you start off with moles of H2. You start off with moles of CO, 1 and 3. You have no moles of the CH4 and H2O because that is the product. And as these two react together, okay, so they're reacting together, it produces this, okay, the products. And so as time goes by, more and more of the H2 is used up, and more of the CO is used up, and more of the product is getting formed. Notice though, once you let it go for a certain amount of time, the amounts of all of these gases kind of level out or plateau, meaning that the concentration or the amount of the moles of these products and reactants start to remain the same. This is the situation of equilibrium, wherein the forward reaction and the back reaction has come to an equilibrium, and so the amounts of the products and the amounts of the reactants do not change. Okay, it's very, very important to remember this. If you want to identify an equilibrium, the amounts of the product and reactants do not change. Okay, that's how you know that the situation is equilibrium. Okay, another way to look at it is rate. If you, instead of moles, you have rate on the y-axis, of course the forward rate is decreasing as more and more of the reactants are used up, and the reverse rate will increase as more and more of the products are formed, and so there is something to reverse, and so eventually you will reach a point wherein the rates of the forward and the back reactions are equal to one another, and so you have reached equilibrium. So another way to look at it is really just a snapshot, okay, of your reaction flask over different time frames. Okay, and I think this is a very, very good way to recognize equilibrium. Okay, so let's say you have this reaction where you have blue ball or blue molecule reacting with the yellow, and it forms this blue-yellow molecule. Okay, so the forward reaction is your blue reacting with your yellow, and it forms this blue-yellow molecule. Okay, what is also happening once you have this? So once you have some product, okay, it will reverse. Okay, and so the competing reaction is the product breaking apart, right? So once you have some product, slowly over time, you will form reactants due to the reverse reaction. Okay. But at some point, the forward and the back reaction will equal one another, and remember, the amounts of products and the reactants won't change. So what is going on here? In the first window at time 0 seconds, you have all starting material, okay? And notice these two react together and it forms this molecule here, okay? And then, as more time continues, these two molecules will form this one here. So you've got, this one, that's this one, okay? And then this one is formed, okay? But notice at 120 seconds, you have two products, and then you have the leftover starting material here, okay? At 240 seconds, notice it's still two products and two of the starting material, okay? Notice in these two windows, the amount of, let me just color coordinate it for you, your blue and your yellow is 2, okay? And the amounts of your singular yellow is 1, and the amount of your singular blue is 1, okay? They're the same, okay? That's how you know that it is reached equilibrium, okay? So this is your equilibrium situation, okay? You're looking for two windows that have the same amounts of reactants and products. So, oftentimes we would like to do a little bit of calculation to see how many moles of each of the reactants and products are at equilibrium. So we have example 14.1, where when you have 1 mole of CO and 3 moles of H2, it's placed in a 10-liter flask and allowed to come to equilibrium. The mixture is found to contain 0.38 moles of water. Okay, so you're putting the CO and the H2 in a container. It comes to equilibrium. At equilibrium, you have 0.387 moles of water. And they would like to know what is the molar composition of the equilibrium mixture. In other words, they want to know how many moles of CO, how many moles of H2, how many moles of CH4, and how many moles of water. Another word to say molar composition is how much moles of each reactant and each product there is in the equilibrium mixture. So how do we calculate that? Okay, the book sets up a little table for you where you have the reaction at the very top of the table, and on the left-hand side you have the starting molar amounts, the starting, the change, and then the equilibrium. Okay, very important to understand that at the beginning you have 1 mole and 3 mole as it was stated in the problem, And at the very, very beginning, you should have no products because nothing has reacted yet. As time goes by, you're going to basically lose some CO and lose 3x of the hydrogen. The reason being that for every 1 CO, 3 hydrogens are required because of this 3 here, okay, stoichiometric coefficient. And when these two react together, you're going to form, for every 1 CO, you're going to form 1 CH4, and you're going to form 1 water because there is an invisible 1 in front of these as well. Okay, so at equilibrium, really what you have in a flask is 1 minus x, x representing how much of the CO has reacted, 3 minus 3x, and again 3x stands for how much of the hydrogen gas has reacted, and it's going to form x and x. X stands for the molar amounts of CH4 and water. Okay, now remember in the problem they tell you that at equilibrium, this is how many moles of H2O you have, okay? So you do know what X is, so let's plug in X into each one of these equilibrium concentrations, okay? Or amounts, okay? Therefore, you have, it's not concentration in this table, I have to get it back, it's mole amounts, okay? So if you plug in X, you're gonna get 1 minus 0.387, so you get 0.163. 3 minus 3 times 0.387, and you're going to get 1.839, so on and so forth. This is what we call the molar composition. Okay. All right. So let's do an example, very much similar to the one we just looked at. Okay. We're in. Suppose you start off with a gas mixture and it has 1 mole of CO and 1 mole of H2O. So what you start with is your initial or your starting amount. The book uses the word initial or starting. I use the word initial. I like the word initial. You'll see why in just a second. Okay. So initially, or at the start, okay, we have 1 mole of CO and 1 mole of water. Now remember, we don't have any products because this is the initial or the start of the reaction, okay? And then you're going to reach equilibrium and you're going to form 0.43 moles of H2. So remember, there is a change that occurs. The change stands for how much of the CO has reacted and how much of the water has reacted. So we're going to say minus X. It is a reactant, that's why it's minus, okay? As it reacts, it should decrease in amount. So we're going to minus X, okay? And we're going to form some amount of CO. That's why it is plus X. We're going to form some amount of CO2 and some amount of H2. So it's going to be plus and plus because those are the products, okay? So at equilibrium, okay, we're going to have 1 mole minus X, the amount that has been reacted, 1 minus X, and then we're going to have X and X, okay? So really, you just have to use the information, the last piece they give you. They say that the mixture at equilibrium contains 0.43 moles of hydrogen, okay? So where's that? At equilibrium, that's this column here, or this row here, okay? We have this much 0.43 moles of hydrogen. Remember, this is hydrogen. Okay, so this is the amount of hydrogen at equilibrium. Okay, so if X is equal to 0.43, so what is the molar composition? The molar composition is going to be 1.00 minus 0.43, and that's going to give me 0.57 moles of CO. And again, it's going to be 1 minus 0.43. Again, that'll give me 0.57 moles of my H2O. Okay, and of course, here we already know it's just X, so 0.43 moles of CO2 and 0.43 moles of the H2. Okay, this is my molar composition. Now, the book introduces this idea of what is called the equilibrium constant. Okay, and we're going to see a lot of this equilibrium constant this semester. And so the equilibrium constant expression, the book defines as an expression obtained by multiplying the concentrations of products and dividing by the concentration of reactants, and raising each concentration term to a power equal to the coefficient in the chemical equation. Okay, so they give you this constant, this equation here, A plus B gives you C plus D, and you have your coefficients, A, B, C, and D in small lowercase letters. Okay, so what they're saying is Kc is equal to the products divided by the reactants. And remember, these are concentrations, these little bracket things. So really it's just the products, C and D, divided by the reactants, A and B. And it's raised to the power, this C comes from this C, this D comes from this D, this A comes from this A, and this B comes from this lower b here. Okay, so this equilibrium constant Kc is really the value obtained for the equilibrium constant expression when equilibrium concentrations are substituted. Okay, and the book says that the law of mass action states that the values of the equilibrium constant Kc are constant for a particular reaction at a given temperature, whatever equilibrium concentrations are substituted. So remember that these values change if the temperature changes. Okay, so Kc tells you, really, is there more product or more reactants at equilibrium, right? Because it really is a ratio, products over reactants. So if it's mostly products, this number is going to be larger than 1. If it's mostly reactants, this number on the bottom is going to be pretty large. So really, Kc tells you whether or not you have mostly products, mostly reactants, or half-half in the mixture at equilibrium, right? If it's mostly products, you're going to have a lot of these numbers. These numbers are going to be large if mostly products. Okay? If it's mostly products, the concentration of C and D will be large, and so Kc will be much greater than 1. Okay? If it's mostly reactants, then A and B will be large. Okay? And if they're about equal, then it really is half products, half reactants. Okay? So think of this as a ratio of products to reactant concentrations at equilibrium. Kc is just a ratio. Okay? So again, I really think pictures help you to understand things. So we're going back to the same picture we were looking at before. We have blue ball, yellow ball, forms blue and yellow together. Okay? So remember, this is the product. These are the reactants. Okay? So really, Kc is calculated by, remember we just said, product, or products, in this case it's just one product, over the reactant concentrations. Okay? So assume that this box is 1 liter, okay, and that every one of these balls is a mole. Okay? And we're assuming that you have a 1 liter flask. Okay? So let's look at the Kc here in the left-hand box. Okay? The Kc is calculated by the product, in this case that's 1, okay, divided by blue ball, yellow ball. So blue ball, there are 2 of them, and yellow ball, there are 2 of them. Okay, and there are no exponents in this case because it's 1 and 1 and 1 in terms of the stoichiometric coefficients. Just 1, 1, and 1. Okay, so therefore the Kc here is going to be 1 times 2 over 2, which is 1 over 4. Okay, or really 0.25. Okay, and it is less than, sorry, my little less than greater than sign mixed up here. It is less than 1. Kc is less than 1. Okay, and when it is less than 1, we say that it is mostly reactants, and it is, right? If you look at it, you've got 4 reactants to 1 product, so it is mostly reactant. And indeed, it is mostly this here, reactants. That's true. Okay. I'm going to go to this next window here. Okay. Here, the Kc is going to be calculated as, okay, again, products, in this case there are two products, so we're going to say 2. And there's one yellow, one blue, so it's going to be 1 and 1. Okay? In this case, Kc is equal to 2. 2 is greater than 1, so therefore Kc is greater than 1. And it's mostly product. Okay? Is that true? Yeah, it is, because look, mostly this stuff, okay, so it is mostly product. Okay? So this is a pictorial representation of literally what we just said mathematically and on how to calculate Kc. All right. So let's just practice writing some equilibrium constant expressions for Kc. Okay. So we're just going to write what does Kc equal to, and it's very important not to forget our stoichiometric coefficients like this 3 here in front of the H2. Okay. So let's do one together. Kc equals the products. Remember, the products are this one and this one. Okay. So we're going to say it is the concentration of CH4 over the concentration of water. And we're going to put it over the reactants. The reactants are these two. Okay. So we're going to say CO and concentration of H2. Okay. Very, very important to keep in mind, since we have a 3 in front of the H2, we're going to put a 3 as an exponent for the concentration of the H2. Okay. If you want, you can pause the video and do the next one by yourself, and then you can unpause it to see if you get this right. Okay, so hopefully you've practiced and done this one. Let's see if you did it correctly. Kc is equal to the product. In this case, the product is the NH3. And your reactants are your N2 and your H2. Okay. Again, very important to keep in mind that you have 1/2 in front of the N2, so you're going to put that as a exponent, and 3/2 for the H2. Okay. So really, where does this whole term or this variable Kc, this equilibrium constant expression, come from? Okay. So this is just a little side note. Okay. The equilibrium constant Kc is actually derived from the rate laws at equilibrium, and the rate laws are from the previous chapter, chapter 13. If you consider the reaction N2O4 becoming 2 NO2s, that's the forward reaction. The reverse reaction would be 2 NO2 forming N2O4. Okay? So at equilibrium, the rate of the forward and the forward reaction would be the same as the reverse reaction. That's the definition of equilibrium. So we would say rate 1, the forward reaction, equals rate 2, the reverse reaction. Okay? If we were to write that, and we write the rate law, right, we would say rate equals K times the starting material N2O4. Okay? And again, for the second reaction, it would be rate equals K times the starting material NO2. Right? And this would be the second order, or the second order, okay? And since these rates are equal to one another, we would say that K of the forward reaction times the concentration of N2O4 equals K times of the reverse reaction times NO2 squared. And the F means forward, R means reverse, okay? If I kind of algebraically manipulated this a little bit, if I divide this side by N2O4 concentration, okay, that would cancel out, okay, and then I would get, I'm going to rewrite it here, Kf equals Kr times NO2 squared all over N2O4, okay, and then if I multiply this by 1 over Kr, and I did the same thing on the other side, 1 over Kr, okay, then really this cancels out, okay, so I have K of F, or actually I get this, K of F over K of R is equal to NO2 squared over N2O4, okay. Kf is a constant, Kr is a constant. Any constant divided by a constant just gives you a new constant, which is we're gonna call Kc. And notice Kc is equal to the product concentration over the reactant concentration. Okay, so really that's how and where we get Kc. Kc is really just the rate constant of the forward reaction divided by the rate constant of the reverse reaction. All right, but the main, this is just a side note of how we get Kc. The real main thrust of this chapter is two things, or this video, sorry, is two things. One, you need to know how to write the equilibrium constant expressions for Kc. And two, you need to be able to solve for the molar composition of the equilibrium mixture. So I'm going to stop the video here. I would go ahead and do the homework on these two main topics before you watch the next video. This is the end of part 1 of lecture 3.